Okay, so we have number one. I've introduced the concept of an ionic compound. An ionic compound contains an ionic bond. An ionic bond is the result of an electrostatic attraction between a cation and an anion. A cation is a positively charged ion that results from the loss of electrons. An anion is a negatively charged group that results from the gain of electrons. Once you've made the cation and the anion, they are going to come together like a magnet. I've also introduced the ions. Group 1, metals form a +1 charge. Group 2, metals form a +2 charge. Silver forms a +1 charge. Zinc and cadmium form a +2 charge. Aluminum, gallium, and indium form a +3 charge. The rest of the metals on the periodic table, you're going to have to either be given the charge or you're going to have a way to determine the charge because they have multiple charges available to them due to their electron configuration. For your nonmetals and metalloids, group 15 forms a -3 charge, group 16 a -2 charge, and group 17 a -1 charge. We then talked about the polyatomic ions. Polyatomic literally means many atom ions. And the majority of the polyatomic ions that you were given are called oxyions because they are an element with oxygen. Now, with respect to your polyatomic ions, you're either stuck memorizing them, or I did give you a way to help you memorize them. But basically, yes, you do have to know them. What we are going to do today is we're going to take those cations that we have discussed and the anions that we have discussed, and we are going to make ionic compounds. Now, just a couple more things about ionic compounds. Number one, they are charge neutral, which means that the extent of the positive has been counterbalanced by the negatives so that the ultimate charge on the molecule is 0. Number two, cations are listed first. In the formula and the name. Of an ionic compound. Okay, we're going to quickly talk about the formation of a formula. Specifically, we are going to talk about how you combine the cations and the anions to make the compound charge neutral. So let's just take sodium and oxygen. Sodium is in group 1, so it always carries with it a +1 charge. Oxygen is in group 16, so it always carries with it a 2- charge. If I were to add this together, +1 -2, the question is, does that equal 0? And the answer to that is no. So that means that sodium does not combine with oxygen in a 1-to-1 ratio. It doesn't combine with oxygen in a 1-to-1 ratio because that would not give a charge neutral compound. Now, is the positive in the lowest quantity or is the negative in the lowest quantity with respect to charge? The positive. We only have one of the positive, whereas we have two of the negative. So let's add another positive to this. Now you have +2 -2. Does that equal 0? Well, yes. So sodium combines with oxygen in a 2-to-1 ratio. We will combine 2 sodiums with 1 oxygen. The quantity is listed as a subscript to the right of the element. So Na2O is the formula. Let's look at one more example of this type, and then we're actually going to get into the way you would actually see it on an exam. Let's combine iron 2 with phosphate. What does the Roman numeral tell me? It tells me the charge. I had to tell you the charge on this iron because iron is one of the metals whose charges can vary. So I'm going to have to be quite specific that it is iron 2. So therefore it is Fe2+. And phosphate ending in ATE means that it is a polyatomic ion. It is the polyatomic ion PO43-. +2 -3, that does not equal 0. So it does not, it is not in a 1-to-1 ratio. Right now, the positive is in the lower quantity, so we're going to add another one. When we do so, we now have +4 -3. That does not equal 0. So it is not in a 2-to-1 ratio. We then add another phosphate because the negative is in the lowest quantity at that point. And so we have +4 -6. That does not equal 0. So it's not in a 2-to-2 ratio. So we add another Fe2+. When we add another Fe2+, we get a +6 -6. That does equal 0. And therefore, 3 iron 2s combine with 2 PO4s to make the compound. The number you need to make the compound becomes the subscript. Now, when you need more than one polyatomic, you place the polyatomic ion in parentheses with the quantity needed outside the parentheses. What this literally is saying is that you need 2 units of PO4. Yes.
I've seen it before, but like I can't remember if it's factored or like with most schools. Like I know that's basically what you're doing, getting like steps like this, but if it's like 2+, then you just need to get that to 6, like kind of coming factor up to 3 and 2.
To a large extent, you are finding the common factor. I'm just breaking it down, and there's also one other piece to it, and I was about to illustrate that. So, no, you're good. You're no worries. I'm just illustrating that the entire goal is when you're developing a formula for an ionic compound, it's got to be charge neutral. The positive has to counterbalance the negative. Now, what we're going to be doing, getting to these formulas, is we're going to go from the name to the formula. And there is a step-by-step method you can use. The first thing you've got to do is you've got to translate the name of the cation and anion into their formula. The second thing you're going to do, and this is the quick way of doing this, is you are going to cross and drop the magnitude which basically is the number on the charge, onto the opposing ion. Finally, you are going to simplify. When needed. Okay, let's look at this in action. So let's take the compound chromium 6 oxide. What does the Roman numeral tell me? Charge on what specifically? The metal. And I had to give you the charge. Why? Because chromium has multiple different charges. Chromium can be a +2, a +3, a +6. You got to tell me which one, or I got to tell you which one. And then oxide, the ending IDE tells me what type of ion is it? What type of anion? Is it an anion of an element, or is it a polyatomic anion? IDE typically is an anion of an element. It's the anion of oxygen. So we have translated the name. Now you're going to take the magnitude and you're going to cross and drop it on the opposing ion. So on our chromium, we're going to drop a 2. On our oxygen, we're going to drop a 6. Then you have to simplify. In this particular case, you will simplify because both of the things that you just dropped are divisible by 2. So this formula becomes CrO3 for chromium 6 oxide. Questions? IDE typically means an anion of an element. There are 3 exceptions: hydroxide, peroxide, and cyanide that I'm making you learn. But IDE typically means an anion of an element. ATE and ITE means a polyatomic. Let's look at another example. Let's look at beryllium perchlorate. Beryllium. What charge is it going to have? It is element number 4 on the periodic table. It's a +2 charge. Why? Because it's in group 2. It is one that is always the same. Perchlorate. What does the ATE tell me? It's going to be a polyatomic, which you got to know, and that's ClO4 -1. Now we're going to take the numbers and we're going to cross and drop them on the opposing ion. So on beryllium, we're dropping a 1. On chlorate, we're dropping a 2. When you drop a number greater than 1 on a polyatomic, what do you do to the polyatomic? It goes in parentheses with the number that you drop as a subscript outside the parentheses. We frequently do not show a 1, so the formula for this compound would be BeClO4 2. Question. That is the name to the formula. Now let's go formula to name. Step number 1. You will identify the cation. As constant charge or varying charge. Because you treat them differently. If it's constant charge, you will name the metal or name the cation. That's which will most typically be a metal, and you will name the anion. But if it's a varying charge, you will name the cation. You will state the charge of the cation as a Roman numeral. In parentheses. And then you're going to name the anion. Now your Roman numerals. As a reminder, 1 is I, 2, I, 3, I, 4 is IV, 5 is V, 6 is VI, and 7 is VII. We don't go past 7. I don't think there's, to my knowledge, there's very few 7s at that. Most of them will be 1, 2, and 3, but there are a few that go higher. Now, in that vent, how do you determine the Roman numeral? Technically, the Roman numeral can be determined with the equation. The number of cations times a variable. You can call it X, Y, Z, whatever, but a variable. Plus the number of anions times the anion charge. And that equation is set equal to 0. Questions? Trying to let people catch up to me. Let's look at all this in action. Let's take AG3P. The question that you're asking is, does the metal have a constant charge or not? Was it one of the ones I gave you? And the answer is that this metal does have a constant charge. It's always a +1. So because it has a constant charge, we name the metal, which is silver, and we name the anion. Phosphorus as an anion gets what ending? IDE. So this would be phosphide. Let's look at another example. Let's look at SNS2. First question, or the question. Constant charge or varying charge? Tens charge varies. So we're going to set up an equation. There is one tin whose charge we do not know. There is two sulfurs, and what is sulfur's charge as an anion? A -2. So we can set up an equation. 1 times x. Whoa. 1x. 2 times the -2 -4. That is equal to 0. X minus 4 equals 0, therefore, so x has to equal 4. So the charge on our tin is a 4. So when we write it, it's 10, 4. And then you say the anion, and since this is an anion of an element, what is the ending? IDE, so this is 10,4 sulfide. Okay, folks, naming and formulas take a lot of practice. It is not something you can wait until the 11th hour to prepare for. Be warned now. You wait until the 11th hour to prepare for this, you will fail the next test. Most likely. It'll put a big dent in your grade. I'll put it that way. So, number 1, there is an optional homework on strictly ionic compounds. I forgot how many questions it had. Number 2, there is a homework strictly on covalent molecules, which we're about to start. And number 3, on a test, it's going to be all mixed up. So there are 2 homeworks. One where I give you something like 118 formulas, and you have to give me the names. And one where I give you like 168 names, and you have to give me the formulas or somewhere in there. It's a lot. Basically, I'm trying to emphasize just how much practice this takes. Now, I realize that people love to save the homework till a few days before the test so they can use it to study for your test. But with 118 and 160 questions, you can do about half of them and still have plenty to do for the test. This one takes a lot of practice. The other thing that I'm going to upload, which I forgot to do, is I will upload a flowchart. It will be a PowerPoint. And the flowchart has questions to ask yourself to help guide you into what type of formula you're working with, or to guide you into what type of naming you need to do. So I will upload that today because I completely forgot about it. Questions so far? But with ionic compounds, if you don't know your polyatomic ions and your ions, you don't know, you're not going to know where to start. Practice. Okay. Now we're going to get into covalent molecules. Covalent molecules have covalent bonds. Covalent bonds arise through the sharing of electrons, which we illustrated when we were developing the Lewis structures for the majority of molecules last week. We shared electrons. How do you recognize a covalent molecule? Covalent molecules will consist of nonmetals and metalloids only. Some key things about formulas. One is that a formula will not be simplified, unlike ionic compounds. If you'll look back at the ionic compounds, I said you're going to translate, cross, drop, simplify. That is only true for ionic compounds. You do not simplify covalent molecules. Now, there are 4 types of covalent molecules that I'm going to discuss today. Well, I'll get started on it. We're going to discuss something that I brought up the other day in the lab lecture. And that is your diatomic elements. The next thing that I'm going to discuss is going to be hydrogen. combined with group 15 through 17 nonmetals and metalloids. After that, we're going to talk about our first and only type of organic molecule. And that is, we're going to talk about alkanes. And I bring up alkanes because whether you're in Chem 1 or Chem 2, a lot of faculty love to ask questions about alkanes. Now, they'll give the formula, but I want you to know what that formula is. And then lastly, we'll bring up binary covalent. Molecules. So let's get into the diatomics. There are 7. They always come in pairs. When found by themselves in nature. There are 2 ways you can memorize the 7. One way is the way I mentioned on the video last week, and that is Brinkelhoff. Bromine, when found in nature all by its little lonesome, is going to come in the form of Br2. Iodine is going to come in the form of I2. So when you get iodine solution, that's what you're usually getting is I2. The nitrogen that is in the atmosphere is N2. Chlorine gas, nasty stuff, is Cl2. Hydrogen, oxygen that you breathe is O2, and fluorine is F2. The other way you can memorize them, I said that there were 7. They form a 7 on the periodic table, and you add hydrogen. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine form a 7 on the periodic table, and then you got to add hydrogen. Diatomic elements simply bear the element name. So Br2 is bromine. O2 is oxygen. so on and so forth. So the question may arise, but, and I can imagine this question, I can see this question. Back in, when we were talking about the periodic table, we said that is oxygen, but that's just a no. And that is oxygen. Which one is oxygen? The fact of the matter is the question shouldn't be which one's oxygen, because technically that is oxygen, the O2. So what is this? O is what you use when you're making a compound. This oxygen is what you're using when you're making a compound, whereas if I'm just talking about pure oxygen that I'm breathing in, that's O2. So the question is there more than one element present, more than one element type present? Then it's O compared to O2. That's all there is to diatomic elements. Okay. When you're talking about hydrogen with a group 15 to 17 non-metal metalloid, the formula can be derived in that the number of hydrogens is equal to the charge on the second element as an anion. So if I say phosphorus, phosphorus has a 3 minus, then the formula is H3P. If I say oxygen, which is O2 minus, then the formula is H2O. Yeah. Any questions? Now for the name. You write the word hydrogen to start. And then you write the second element as an anion. This is going to be true with one exception. That exception is H2O, which will always be water. It does not, in my book, it does not have another name. I will count it wrong if you give me another name. That's because across the entire world, everybody knows it as water in that language. And that's what naming is all about, is for somebody over in Switzerland to be able to recognize a compound based off of its name. And therefore we have to use the same naming system from one continent to the next continent. That's what naming's all about. That's supposed to be a 2. Why did it do that? I don't know. Okay, so for example, our H3P, you're going to write hydrogen, and then you're going to write the second element as with the ending IDE. So that's hydrogen phosphide. HCl, you're going to write hydrogen, followed by the second element as with the ending IDE. So that's hydrogen chloride. Questions? Okay, I don't have time to get into alkanes. So I'll have to pick that up on, I'll have to look at how everything is panning out, but probably Thursday.